the electromagnetic radiation emitted when charged particles are accelerated radially. The users can select the wavelength required for their experiment. High flux, high-intensity photon beam allows rapid experiments or use of weakly scattering crystals. High brilliance, highly collimated photon beam generated by a small divergence and small size source. High stability, submicron source stability. Polarization, both linear and circular. Pulse time structure, pulse length down to tens of picoseconds allows the resolution of process on the same time scale. Emission mechanism, when high-energy particles are in rapid motion, including electrons forced to travel in a curved path by a magnetic field, synchrotron radiation is produced. This is similar to a radio antenna, but with the difference that, in theory, the relativistic speed will change the observed frequency due to the Doppler effect by the Lorentz factor. Relativistic length contraction then bumps the frequency observed in a lab by another factor of, thus multiplying the GHz frequency of the resonant cavity that accelerates the electrons into the X-ray range. The radiated power is given by the relativistic Lama formula, while the force on the emitting electron is given by the Abraham-Lorentz-Dirac force. The radiation pattern can be distorted from an isotropic dipole pattern into an extremely forward-pointing cone of radiation. Synchrotron radiation is the brightest artificial source of X-rays. The planar acceleration geometry appears to make the radiation linearly polarized when observed in the orbital plane, and circularly polarized when observed at a small angle to that plane. Amplitude and frequency are however focused to the polar ecliptic. Synchrotron radiation from accelerators. Synchrotron radiation may occur in accelerators either as a nuisance, causing undesired energy loss in particle physics contexts, or as a deliberately produced radiation source for numerous laboratory applications. Electrons are accelerated to high speeds in several stages to achieve a final energy that is typically in the GeV range. In the LHC, proton bunches also produce the radiation at increasing amplitude and frequency as they accelerate with respect to the vacuum field, propagating photoelectrons, which in turn propagate secondary electrons from the pipe walls with increasing frequency and density up to 7 by 1010. Each proton may lose 6.7 keV per turn due to this phenomenon. Synchrotron radiation in astronomy. Synchrotron radiation is also generated by astronomical objects, typically where relativistic electrons spiral through magnetic fields. Two of its characteristics include non-thermal power, law spectra, and polarization. History of detection. It was first detected in a jet emitted by Messier 87 in 1956 by Jeffrey R. Burbage, who saw it as confirmation of a prediction by Joseph S. Shklovsky in 1953, but it had been predicted earlier by Hannes Alfvén and Nikolai Herlofsson in 1950. T.K. Briers noted that questions of priority on the history of astrophysical synchrotron radiation is complicated, writing. In particular, the Russian physicist V.L. Ginzburg broke his relationships with I.S. Shklovsky and did not speak with him for 18 years. In the West, Thomas Gold and Fred Hoyle were in dispute with H. Alfvén and N. Herlofsson, while K.O. Kiepenheuer and G. Hutchinson were ignored by them. Supermassive black holes have been suggested for producing synchrotron radiation by ejection of jets produced by gravitationally accelerating ions through the supercontorted, tubular, polar areas of magnetic fields. Such jets, the nearest being in Messier 87, have been confirmed by the Hubble telescope as apparently superluminal, traveling at 6 times c from our planetary frame. This phenomenon is caused because the jets are traveling very near the speed of light and at a very small angle towards the observer, because at every point of their path the high-velocity jets are emitting light. The light they emit does not approach the observer much more quickly than the jet itself. Light emitted over hundreds of years of travel thus arrives at the observer over a much smaller time period, giving the illusion of faster-than-light travel. There is no violation of special relativity. Pulsar wind nebulae. A class of astronomical sources where synchrotron emission is important is the pulsar wind nebulae, aka Lorentz, of which the Crab Nebula and its associated pulsar are archetypal. Pulsed emission gamma-ray radiation from the Crab has recently been observed up to 25 GeV, probably due to synchrotron emission by electrons trapped in the strong magnetic field around the pulsar. Polarization in the Crab at energies from 0.1 to 1.0 MeV illustrates a typical synchrotron radiation formulation. Leonard-Wickett field. We start with the expressions for the Leonard-Wickett field, where which is the unit vector between the observation point and the position of the charge at the retarded time, and is the retarded time in equation, and the first terms fall off as the inverse square of the distance from the particle, and this first term is called the generalized Coulomb field or velocity field. If we ignore the velocity field, the radial component of Poynting's vector resulted from the Leonard-Wickett field can be calculated to be. Note that the spatial relationship between and determines the detailed angular power distribution. The relativistic effect of transforming from the rest frame of the particle to the observer's frame manifests itself by the presence of the factors in the denominator of EQ. For ultra-relativistic particles, the latter effect dominates the whole angular distribution. The energy radiated into per solid angle during a finite period of acceleration from to is integrating EQ over the all-solid angles. We get relativistic generalization of Lamar's formula. However, this also can be derived by relativistic transformation of the 4 acceleration in Lamar's formula. Velocity acceleration. Synchrotron radiation. When the charge is in instantaneous circular motion, its acceleration is perpendicular to its velocity. Choosing a coordinate system such that instantaneously is in the z direction and is in the x direction, with the polar and azimuth angles, and defining the direction of observation, the general formula EQ reduces to in the relativistic limit. The angular distribution can be written approximately as the factors in the denominators tip the angular distribution forward into a narrow cone like the beam of a headlight pointing ahead of the particle. A plot of the angular distribution shows a sharp peak around θ equals 0. Integration over the whole solid angle yields the total power radiated by one electron, where E is the electron energy, B is the magnetic field, and ρ is the radius of curvature of the track in the field. Note that the radiated power is proportional to, and, in some cases, the surfaces of vacuum chambers hit by synchrotron radiation have to be cooled because of the high power of the radiation. Using where as the angle between the velocity and the magnetic field, and r as the radium of the circular acceleration. The power emitted is. Thus the power emitted increases with the energy to the fourth and decrease with the radius to the square and the mass to the fourth. This radiation is what limit the energy of an electron-positron circular collider. For a proton-antiproton collider, the energy is limited by the maximum magnetic field. This is why the LHC has an energy only 70 times higher than the LEP, even though the mass of the proton being 2,000 times higher than the mass of the electron. The energy could be 2,000 times higher to have the same synchrotron radiation. Radiation integral. The energy received by an observer is using the Fourier transformation. We move to the frequency space, angular and frequency distribution of the energy received by an observer. Therefore, if we know the particle's motion, cross products term, and phase factor, we could calculate the radiation integral. However, calculations are generally quite lengthy. Example 1. bending magnet integrating trajectory of the arc of circumferences in the limit of small angles we compute substituting into the radiation integral, and introducing, where the function is a modified Bessel function of the second kind, frequency distribution of radiated energy from EQ, we observe that the radiation intensity is negligible for critical frequency is defined as the frequency when in so, uncritical angle is defined as the angle for which n is approximately for frequencies much larger than the critical frequency and angles much larger than the critical angle. The synchrotron radiation emission is negligible. Integrating on all angles, we get the frequency distribution of the energy radiated. If we define where, then, note that, if the formula for spectral distribution of synchrotron radiation, given above, can be expressed in terms of a rapidly converging integral with no special functions involved by means of the relation synchrotron radiation emission as a function of the beam energy. First, define the critical photon energy as then. The relationship between radiated power and photon energy is shown in the graph on the right side. The higher the critical energy, the more photons with high energies are generated. Note that there is no dependence on the energy at longer wavelength. Polarization of synchrotron radiation in EQ. The first term is the radiation power with polarization in the orbit plane, and the second term is the polarization orthogonal to the orbit plane. In the orbit plane, the polarization is purely horizontal. Integrating on all frequencies, we get the angular distribution of the energy radiated. Integrating on all the angles, we find that 7 times as much energy is radiated with parallel polarization as with perpendicular polarization. The radiation from a relativistically moving charge is very strongly, but not completely, polarized in the plane of motion. Example 2. Undulator solution of equation of motion. An undulator equation. An undulator consists of a periodic array of magnets, so that they provide a sinusoidal magnetic field. Solution of equation of motion is where and the parameter is called the undulator parameter. Condition for the constructive interference of radiation emitted at different poles is expanding and neglecting the terms in the resulting equation. One obtains for one finally gets. This equation is called the undulator equation. Radiation from the undulator radiation integral is using the periodicity of the trajectory. We can split the radiation integral into a sum over terms, where and the radiation integral in an undulator can be written as the sum of generates a series of sharp peaks in the frequency spectrum harmonics of fundamental wavelength, and depends on the angles of observations and on the axis. The radiation integral becomes n, where note that only odd harmonics are radiated on axis, and as k increases higher harmonic becomes stronger. A radio antenna, but with the difference that, in theory, the relativistic speed will change the observed frequency due to the Doppler effect by the Lorentz factor. Relativistic length contraction then bumps the frequency observed in a lab by another factor of, thus multiplying the Gh frequency of the resonant cavity that accelerates the electrons into the X-ray range. The radiated power is given by the relativistic, the electromagnetic radiation emitted when charged particles are accelerated radially. The users can select the wavelength required for their experiment. High flux, high-intensity photon beam allows rapid experiments or use of weakly scattering crystals. High brilliance, highly collimated photon beam generated by a small divergence and small size source. High stability, subbeam, and circularly polarized when observed at a small angle to that plane. Amplitude and frequency are however focused to the polar ecliptic. Synchrotron radiation from accelerators. Synchrotron radiation may occur in accelerators either as a nuisance, causing undesired energy loss in particle physics contexts, or as a deliberately produced radiation source for numerous laboratory applications. Micron source stability, polarization, both linear and circular, pulse time structure, pulse length down to tens of picoseconds allows the resolution of process on the same time scale. Emission mechanism. When high-energy particles are in rapid motion, including electrons forced to travel in a curved path by a magnetic field, synchrotron radiation is produced. This is similar to a Balmer formula, while the force on the emitting electron is given by the Abraham-Lorentz-Dirac force. The radiation pattern can be distorted from an isotropic dipole pattern into an extremely forward-pointing cone of radiation. Synchrotron radiation is the brightest artificial source of X-rays. The planar acceleration geometry appears to make the radiation linearly polarized when observed in the orbital plane.